Good afternoon. Hi, everyone. Welcome back to our session number 3 for the afternoon. In the session, we're going to be talking about microtunneling and tunneling case studies. I would like to introduce our first speaker this afternoon. His name is Brandon Gorr. He is coming to us from our Markham office in Ontario. Brandon has over 10 years of experience working as a civil municipal infrastructure engineer. Brandon has worked on many wastewater treatment projects, wastewater collection systems, storm water design, water treatment plants, water distribution systems, and land development. Brandon's ideal vacation is where he flaunts his fitness abilities by running ultra marathons anywhere in the world. So here is to present on the East Brampton Microtunneling Project, Brandon Gorr. Brandon, are you ready?
Ready. Thanks, Linda. It was my fitness abilities before COVID was a thing. So perfect. Well, thanks everybody for making it to the presentation here this afternoon. I want to discuss our project here with the Region of Peel, the 20 of the East Brampton Trunk Sewer Project. So this was a 5.4 kilometer microtunneled trunk sewer that was, as the name says, twinned to an existing 1350 trunk sewer. And here's I guess the case study of what we've done. To give you an outline of what the background of the project is, or what we're going to be talking about, we're going to be talking about the background of the project, what really spawned this project from occurring, the project overview of what Associated's role was in this project, and some of the new regional design standards that are being implemented on this project. So I'm going to give you some background information. The Region of Peel, through some initial asset management assessments, had identified that their systems weren't operating as well as they believe they should. And they identified that the inflow and infiltration was coming to be a major problem with some of their sanitary collection and treatment systems. So an action plan was developed by the region to reduce the potential sources of inflow and infiltration from a variety of sources. Some inflow sources can be for instance, a storm sewer that is overloaded or surcharging, and it has a relief line into the sanitary trunk sewer. You have residential buildings or residential houses that are pumping directly their sumps into this sanitary sewer. So you got to cut those off. But some other areas where they were seeing a lot of water ingress into the system was due to infiltration through cracked or broken pipes, deteriorated chambers and manholes, and separated pipe joints in the collection system. And this graphic here on the right here isn't from the Region of Peel's project, but it kind of goes to show that even one small joint here, and it doesn't even have to be an aging infrastructure, even some of the newly constructed projects here, if it's not installed properly, can have a lot of leaky joints. And as you can see here, like it can accumulate into the collection system and really reduce your capacity. And this is just one joint. So, this is a major concern here for the region, and a major concern. So as we're going on here, like what is the concern with I&I is that it increases the burden of the sanitary collection system and the treatment systems as well. The need for additional infrastructure, additional collection systems, even increased treatment systems as well. And of course, then the increased maintenance costs that go along with that. And so then there's also an increased cost here to treat the water, and it is fairly high to treat essentially groundwater that's coming into their system. And it also increases the potential for environmental spills and basement floods just to an overloaded system. So if you see the picture here on the right, this is actually from the project itself, and it was actually during a melt season that was happening here in the spring. And under normal operating conditions, it wouldn't be this high, but you get an idea or a feel for just how severe some of this inflow and infiltration was occurring and how much it impacted the system. It looks like it's just about to crust there. So for the project overview, the Region of Peel then retained AE to design the 5.4 kilometer sanitary trunk sewer to twin the existing 1350 trunk sewer. So the new design consisted of 1,500 millimeter and 1,800 millimeter diameter concrete pressure pipes. And the plan was for the region was to divert the flows from the existing 1350 over into the new trunk sewer. So what they can do then is they can get into the 1350 and kind of do an assessment of how bad the condition of the pipe is, if they need to really replace the 1350, what they can do to restore that and take care of the inflow and infiltration. So if you look at here, they also had 36 chambers that compose of precast and cast-in-place concrete structures. So for those of you who aren't really familiar with the GTA or portions of the GTA here, you can see is obviously a heavily dense or very dense area. And this is the location where our project was in East Brampton. To give you an idea of our proposed concept, we had just to here, if you can see the green dot at the bottom of your screen, that's where the new trunk sewer is going to tie into the existing trunk sewer. And here's our alignment that we chose to take to twin the system. And then it tied into an existing force main just at this intersection here of Queen and Goreway Drive. So as you can see, it's a very, very dense area. A lot of businesses, a lot of arteries here, a lot of highways, and a lot of stakeholders here too. So for some of these stakeholders, we had the Toronto Regional Conservation Authority. We were crossing a number of environmental streams and creeks. And they wanted to make sure that our project wasn't negatively impacting the environment. We had the 407 ETR, which is essentially a relief line to the 401, but an expensive relief line at that, that we had to cross. So major infrastructure there as well. Industrial businesses that were along the backside of our alignment. And these were, major industrial businesses, and we just couldn't impact their operations with our construction. So we had to really work hand in hand with some of these stakeholders here to make sure there's no conflicts. We have the city of Brampton. Here there's a storm channel at this location here where, again, a lot of the storm waters were conveyed to the environment. And so we couldn't disrupt that as well. We had the Cian rail yard, which is one of the major distribution or transportation hubs here in the GTA. This rail yard would be essentially a transition point from rail or freight to semi-trucks and deliveries on the road. So you'd have traffic along these intersections day and night, and heavy traffic. So we had to work hand in hand with CN to make sure that we didn't disrupt their business either. And again, tunneling underneath the CN tracks. Again, you can tell by the number of spur lines that we have just above this arrow that it is a fairly important hub here in the GTA. And so we had to make sure that these tracks were not negatively impacted. And then further up, another stakeholder here was the Goreway Power Station, which helped power and provide power to all these businesses and consumers here. So we had to make sure that we didn't impact their infrastructure too, and their underground infrastructure when we were installing our trunk sewer. We had another stakeholder here at DESA, which was essentially a car auction auto lot. This is for all the dealerships or some dealerships here in the GTA. And essentially you'd have this entire area loaded with vehicles on a Monday, Tuesday. But Wednesday, the auction would happen and to have everybody come to these grounds. And Thursday, Friday, the lot was cleared out with whoever had purchased the vehicles and then ready for the next week to start again. So again, a lot of congested, a lot of business going on here that we just couldn't negatively impact. And just based on the DESA's inventory, there was a lot of security concerns, obviously, because there are a lot of vehicles there that were worth a lot of money. So we had to make sure that our project was staged properly, or worked with DESA to make sure that their business wasn't impacted from a security point as well. And then looking up at the final intersection of the tie-in connection here was with the city of Brampton. And even on a good day, these are pretty congested roadways. So we had to make sure that our construction was very not disruptive to the area. So a lot of important stakeholders here that we had to contend with. So again, there was a lot of negotiations here with the stakeholders, seeing how we can work this project to make sure that it didn't negatively impact them. So the design of this project was actually awarded to AE in 2013. And then in February of 2017, the project was tendered and awarded to the contractor. The project was completed actually ahead of schedule in January 2019, just after the new year. And we're actually heading into the warranty period, or ending the warranty period here in the next couple months without any, knock on wood, issues. So the total construction cost was about $50 million. So as we're discussing here, the region was really concerned about these inflow and infiltration issues that they were having. So they decided to work with AE, or we worked with the region to develop these new standards and implement these new standards. And this was at the infancy stage of these new standards being developed. Since then, the region has obviously taken it and further developed it, and they're great standards now for reducing inflow and infiltration. So some of the factors, again, with these new designer standards were to mitigate the infiltration, and it was to focus on a variety of factors. But for this presentation, we're just going to discuss the pressure testing of this pipe and the pipe material itself. So the sanitary sewer, which was a gravity sewer, was pressure tested. People were thinking, well, why would you pressure test a gravity sewer? And that's, of course, to assure that the sanitary sewer is watertight and that you don't have these ingress or infiltrations from groundwater from outside sources. And also to provide the capacity, the ability to surcharge if the need arises to in the future. So again, to confirm that the system was watertight, the system was pressure tested to 50 psi for 2 hours without a pressure drop, without any pressure drop. So they had to use make-up water calculations based on AWWA M9 standards. So as part of the contract and as part of the new design standards, the region required the use of C302 concrete pressure pipe. And this is something that's most commonly, or not as commonly, used in Southern Ontario as opposed to C300 or C301. And those are more for water main installations, just because they have a higher pressure capacity with them. But regardless, we want to look at the maximum jacking loads that we're going to be looking at here that's going to be exhibited on these pipe. So what we want to do is we want to determine, well, what is the pressure at the face of the tunnel, and what is the estimated skin friction on the entire pipe string that we have to overcome to keep this microtunneling pipe moving forward. So looking at this, I promise this is going to be one of the only screens here with a lot of numbers on it. But for this example here, we're just going to look at the average water pressure at the tunnel. And this is your hydrostatic pressure that's pushing against the face of the TBM. And then you look at your horizontal earth pressure on the face of the TBM as well. So you combine these together, and this is what your pressure is going to be for at the face of the TBM for stability. And then you look at your pipe circumference. You want to look at your skin friction and determine what type of skin friction forces you need to overcome to keep this string moving. So you look at your pipe circumference. You multiply that by obviously your interface friction value, which is given to you by your geotechnical consultant. The length of the tunnel, obviously, and you can understand or determine your estimated skin friction values you need to have to overcome to keep this string moving forward. So combine that with the pressures and the forces that are needed to maintain stoil stability at the face, and you can get your estimated jacking force. And for this example, it's about 215 tons. So then you take this and you compare this to your axial forces of your pipe, or your permissible jacking forces for your pipe. And this is determined in accordance to ASCE 2717. And so this is what we had done for this example. We'd used a typical C302 pipe and determined what type of jacking loads can be exerted on this pipe that are allowable. So for this example, what we'd done is we'd, again, taken the typical C302 pipe and looked at the jacking forces, and we had about a 500 ton that was allowable. So looking at the other example we had previously, the estimated jacking loads for that was about 215 ton. So we had about twice as much capacity as we needed, which is great. But there are obviously some times where your pipe string requires a lot more force than the permissible jacking forces allowed on the pipe. So what do you do in those situations is you can divide up the jacking loads over the string of pipe by installing interjacking stations. So what this does is it takes essentially the jacking equipment from the rear of the tunnel and moves it forward to create essentially a new string in front of the pipe that was just installed. So you can also determine the number of interjacks that are required, obviously just based on your pipe string and how much force is needed to keep the pipe string moving, and determine your maximum axial forces allowable on your pipe. However, there is a tipping point where the number of interjacks of the tunnel is just economical if you start adding 4 or 5 interjacks onto it, because these can be very, very expensive shafts to construct. Some of the minimum costs for some of these are about $500,000 just to install a shaft. They can range up to a couple million too. So quickly escalates the price of the project here. So the contractor had looked at it and said, well, is there a potential that we can enhance the C302 pipe? The region has stipulated that a C302 pipe had to be utilized. However, can we enhance it? And for this example, or what they intended to do, was they wanted to thicken the walls of the pipe. And so what we had done is we'd done some calculations here to determine if you are to thicken the walls, what does that allow for resilience for jacking loads, given the minimum C302 requirements, and then comparing it to what they had put forward as an alternative, or what they wanted to do to enhance it. So we had done a comparison of these on a number of different factors here, and determined that, yeah, if you would like to, you could thicken the walls of the pipe and have larger axial forces on the pipe. And so because the contractor opted to use microtunneling methodologies for the entire trunk sewer installation, there were a bunch of very tight curves along the sewer alignment, and there was a potential for joint separation to be considered, or had to be considered. So if you look at this example here, this is your typical C302 pipe Carnegie joint. And now as you start to go around a corner and start to make a curve, these joints begin to deflect and separate. And it allows, obviously, fines as you're jacking the pipe to move in between these joints, and over time and over the length of the pipe, or the length of the string, can separate these joints to a point where they can be inches wide. And it essentially is a void in that location. So given that the region also wanted to have this pipe pressure tested to 50 psi, the contractor had said, well, hey, what can we do? Can we enhance this joint, make it a better joint? And so what they had done is they had talked with their pipe manufacturer, and they said, well, here's your typical AWWA C302 joint. And what if we take some components here of a concrete and steel joint, combine these together, and create an enhanced joint configuration here? So what they're trying to do is they still met the requirements of a C302 pipe Carnegie joint, but it was essentially enhanced now that they had the steel collar, and it had 2 gaskets here on that steel collar that could prevent a seal against the collar to prevent fines from coming in, and as well make sure that the pipe could be pressure tested to 50 psi. So here's working with the region again, and working with Associated, the contractor, and the pipe manufacturer. They had enhanced this joint configuration. Here's the product here that they had produced. So the development of the enhanced C302 joint assisted in completing actually one of the tightest microtunneled curves in North America, with a radius of about 153 meters. And that was at the time, and I don't know if this has been overtaken yet, but To give you an example, what a 153 meter radius looks like, on some of our as-built drawings, you can see right here just how tight that curve is. And the contractor did, again, have to pressure test this pipe to 50 PSI. And so it did pass on the first attempt as well. So it worked. It was perfect. It was good. And again, here's talking about some of the pressure testing that was completed here for the trunk sewer itself. So just some of the operations and how we're able to pressure test the pipe. And some additional key milestones, though, is because they're also able to thicken the wall of the pipe, of the C302 pipe, they're able to drive microtunnel lengths up to 600 meters. So because of this, because they're able to adjust these wall thicknesses and increase the axle loads, this actually eliminated 16 shafts, intermediate and jacking shafts. So it actually was fairly economical here to do that. And it worked out great. So again, this was a collaborative project here with the project team, with the owner, the contractor, and everyone here to provide a quality product that is economical and meets all the intended purposes here. Again, this is kind of illustrating here just that it is imperative that you have a designer who has the knowledge and understanding of the trenchless design, so that they can, it's not just a line on the drawing here, that if a change comes up, that they can discuss it and they can analyze it as well. So similar to what Sam had just mentioned here this morning, if you were in the morning sessions, a knowledgeable designer is a key to a successful project. So we believe that working with the contractor and the owner and AE, this was a very successful project. So I give some acknowledgements here to a few individuals here. Mr. Anthony Parente with the Region of Peel, who is the main person responsible for mandating new construction standards, and to our trenchless design team here, Mark Belanger and Cian McDermott, who were instrumental in the design and analysis of these alterations. So thanks everyone for coming to the presentation. Opening the floor here to take any questions or comments. And yeah, thanks for coming to our project, our presentation.
So we have a couple of questions that has come in. Gabriel Jean asked, would a stainless steel band be better than a zinc band at the joints?
Well, we wanted to, I think, to use that zinc joint just for the ability to, I guess, actually that was for the inside. I think that the stainless steel would have to be actually an analysis to see which would be a better product. Cost comparison, I think, would be the main factor here. So something that we could look at. Yeah, that's an alternative too, potentially.
Good. Melanie Gray asked, did you pressure test with air?
No, we actually pressure tested with water from a water source. So similar to like a water main, what you would do is we filled it from hydrants and pressure tested it with water, actually, yeah.
How successful was the pressure test?
It was great. It actually was flawless. It was within all allowable limits every time. There was no issues at all for each one of those drives, for each one of those tested sections. I think there's probably about a dozen they tested at a time, or a dozen they had tested individually, sorry. And yeah, it passed flawlessly on every time, so on every occasion. Yeah.
Andrew Stewart from Edmonton asked, how was the pressure test pressure determined?
Like what was the, why did they say 50 psi as opposed to like 100 psi? Well, this is something that the region wanted to, that was their mandate, that was their standard that they wanted to develop. So that was a requirement that they had done. I wasn't part of understanding why 50 psi was the main pressure test, but I'm sure it's because of the C302 pipe requirements as well, right? That would be one of the maximums of the C302 pipe.
Anya has asked, how many shafts were built in total? in this project?
There was a number of shafts, about 18 shafts, 18 shafts that were actually constructed. Some of these were obviously just launch shafts or retrieval shafts. Some of these were also converted into cast-in-place chambers as well. So there were, about 18 shafts.
Rulian Gu said, what was the cost implication of the pipe enhancement?
It's with the pipe enhancement because it allowed them to increase their tunnel drives. Sorry, the cost was actually given back to the contractor with the enhancements that they were able to provide. They were able to give us credit back to the region for removing of these interconnecting chambers, interjacking chambers and shafts. So it was essentially a fair trade here. So.
Cool. I hope that answers everyone's questions. And if, oh, okay, I see another one here. Curious if any problems were encountered with the 600 meter drive lengths.
No, there wasn't actually. It was obviously then just the contractor had said they had encountered a few boulders. That was it. It wasn't anything with anything severe with the pipe getting stuck or anything like that, or the tunnel or the pipe string getting stuck. There was no issues. No.
Another question from Chris O'Donnell here. Was the construction 24/7?
Yeah, for some of the tunnel operations, it was 24/7. They didn't want to have that tunneling operation stop even for 12 hours, because then again you get your soils that'll start to, I guess, clamp down essentially on your can of your microtunneling machine, and it's just that much more forces you have to overcome if you want to get that moving again the following day. So it was 24 hours, yes.
Cool. Thank you so much, Brandon. That's all the questions. All right. Next up, we have Cian McDermott coming from our Markham, Ontario office. Cian has over 12 years of international engineering experience, starting in Ireland, Australia, then finally landing in our Markham, Ontario office. Cian's international engineering experience has enabled him to bring innovative design concepts and construction practices to the projects that he's involved in. As a new Canadian citizen, Cian still owns his Irish accent, and its deep, smooth qualities has been described to have the ability to make a Wolverine purr. So please enjoy it in this next presentation on the Zone 4 tunneling project. Thank you.
Thank you, Linda, for that introduction. Good afternoon, everybody. In this presentation, we will review a common tunnel industry issue. And that issue is, how do we reimburse contractors when they encounter boulders during pressurized face mining? So in other words, how can we pay the tunneling contractor for obstructions when we can't physically see or quantify those obstructions? We encountered this issue on a recent Trenchless project in Milton, Ontario, that we completed with the region of Halton. We will go through this project in today's presentation, and we will discuss how we developed a fair and equitable pay item for the contractor for when they encounter these boulders. So the pay item was, I should note here that the pay item was collaboratively developed with input from the contractor, the owner, and the consultant. And all of this was after the tender and during construction. So it's important to note that. So here's a brief outline of what we will be discussing over the next half hour. We will give a general project overview, and then we will get into the ground conditions and the subsequent geotechnical baseline reports and the tender boulder unit item. Following this, we will go through the contractor's preferred equipment, and as a result, how we had to ultimately develop a pay item for their equipment. We will then wrap up the presentation with some conclusions, and hopefully we will have some time at the end for a couple of questions. So, project overview. So the overall project included about 12 kilometers of 1200 millimeter and twin 900 millimeter diameter water mains. And this was to be installed by a combination of open cut methodology and a variety of different trenchless methods across this 12-kilometer stretch. However, this presentation today, we will focus exclusively on a 2.4-kilometer section of the 3.5 meter diameter air pressure balance tunnel. So this 2.4-kilometer section was split into 3 separate sections separated by intermediate shafts. Other key information is the majority of the alignment is through halting glacial tills with some mixed phase conditions, which is typical for tunneling in the overboard in the GTA area. It's important to note that the contractor did utilize a 3.5 meter diameter Lovett air pressure balance machine. The cutter head did just have rippers and scraper tools only, i.e. no disc cutters, and the tunnel liner was segmental liners. So I'll just get my, I'll try to get my laser pointer out here, but just to give you an idea of where this project is. So this project is in Milton, Ontario, which is about 50 kilometers west of the city of Toronto. This highway that you can see in the center of your screen here is Highway 401, busiest highway in North America. At this exact location, it's probably, I think it's like 8 lanes. The top of the graphic here will be north. So to the north of the highway, we had 1 intermediate shaft. And then to the south of the highway, we had a 2nd intermediate shaft. So as I said previously, this 2.4 kilometer stretch of tunnel was split into 3 separate drives. So south of this shaft, we had an approximately 1 kilometer drive. Crossing of the highway was approximately 400 meters. And then the remaining section to the north was an additional 1 kilometer. So this section to the south is where we developed with the contractor this alternative pay item. So now that we have an understanding of where the project was, let's get an understanding of what the ground conditions were. So the investigation noted that there would be mixed phase soil conditions with a high frequency of cobbles and boulders. I should note, while the frequency of boulders was expected to be high, the actual volume of boulders compared to the excavated material was expected to be quite low, and our geotechnical subconsultant estimated this at a volume ratio of 0.221%, which we would consider as trace amounts of boulders. The ground conditions would be mixed phased with variations of plastic and non-plastic glacial tills, with some isolated sand lenses expected to be encountered. The plastic soils would have low to medium clogging potential. The water table would be 2 meters above ground south of the highway, so that shaft that we noted just south of Highway 401 was under artesian pressure, so the water table would come up 2 meters above ground once we excavate it. The boulder unconfined compressive strengths were in excess of 200 MPa, and we did find boulders in both of the shafts that I just showed you on the previous slide. They were in excess of 900 mil. They were made from granite, and we did do some core sampling on them, and they were in excess of 200 MPa. So this was a good check for the GBR on this one. So we did field verify the strength of the rock in this case. So moving on to the GBR and tender items, what do we baseline for this contract? So we baselined the boulder ratio, the strength, type of boulders anticipated to be encountered, the typical soil characteristics, including clogging potential of the plastic soil material, boulder quantity, distribution, and we also baseline some hydrogeological parameters. If we take a look at the table just to the bottom right of your screen, I will attempt here to zoom in and make it bigger so everybody can see it a little bit more clearly. So we take a quick look at the baseline boulder quantities in the table. It's important to show this because this is going to be the basis of how we developed our pay item. Our geotechnical sub-consultant developed this boulder distribution table, and it was based on a size frequency histogram developed based on data collected from the Shepherd subway tunnel construction in Toronto. So you can see here to classify boulders all the way from 300 to greater than 900 in increments of 150 mil. We don't classify boulders less than 300 because we consider them incidental or cobbles. The other thing that they've done was to put in, we'll say we take the first tunnel drive for an example on the top line there, it says 113 to 114, which represents the first tunnel drive, which was between shaft 113 and 114. Based on the histogram, it was predicted that boulder, if you want to look at these as buckets, so the boulder bucket between 300 and 450 mil, we would expect to encounter 309 of these boulders, which as a boulder volume ratio will be quite small, but as a frequency will be quite frequent. And you can see the same for 450 to 600 and so on and so forth, 37, 9, 3. And we expected to find boulders greater than 900, just one on this entire length. So all this information was derived from, there's many studies done on the Shepherd subway tunnel, and it was based on information gathered as part of that mining process and excavating of the shafts. And that's how a lot of the geotechnical baseline reports and quantities for boulders are estimated in the Greater Toronto area. So here is an example of the stratigraphic profile included in the geotechnical baseline report. So what it does is it effectively shows the various soil types and where the tunnel bore machine is expected, or what the tunnel bore machine is expected to effectively drill through. So on the profile there, you'll see those dashed black lines, and that represents the vertical alignment of the tunnel. As you can see there, it passes through a number of different colors. And each of these colors represent soil classes. So the gray area at the very top would be a Class A fill. The yellow would be Class B sands. Orange would be Class C silts. The brown would be the Class D non-plastic till, and the green would be the Class F plastic tills. But for all intents and purposes here, our tunnel alignment primarily goes through the Halton tills, whether it's like the plastic or the non-plastic, and then with some sand lenses in very specific locations. So as part of the contract, we did include a boulder unit price, and this was agreed with the region at the time. As we said, this is a 14-kilometer long project. There's many different types of tunnel methodologies used on it. So the contract provided a provisional pay item for a volume of boulders removed in cubic meters. And of course, this is only for the volume received above the baseline volume specified in the baseline report. The pay item issue that derived as part of this was boulders encountered could not be recovered due to the machine breaking, fracturing, crushing the boulders into smaller pieces. So kind of as we said earlier, how can we pay a tunneling contractor for obstructions that we can't physically see or quantify in terms of volume removed? Subsequently, an alternative pay method of quantifying the boulders encountered and paying for the encounters was required, and we had to come up with that during construction. So the contractor's tunnel boring machine. So I think prior to discussing the development of the pay item, it's important to understand the contractor's mining equipment. So on the screen there, hopefully you can see this is a drawing of the contractor's 3.5 meter diameter air pressure balanced tunnel boring machine. I'll just get my laser pointer right here. So what happens is the tunnel bore machine, as it advances forward, the cutter head will excavate the material in front of the machine. The material will get ground down and it will go through the cutter head of the tunnel boring machine, and it will then enter into this mixing chamber where it will get mixed with whatever soil conditioners or additives that the contractor is using. And the surplus excavated material plus these additives kind of come up with toothpaste-like consistency, which allows the contractor to effectively maintain pressure at the face of the machine by using earth pressure balance. And as the material gets mixed here, the screw conveyor that we can see here will screw the material from the mixing chamber and take it out ultimately to the muck carts and ultimately dispose off site. I think it's important to note before we proceed that this actual screw conveyor is kind of like the limiting factor here, and the primary reason why we had to develop this additional pay item. So this drawing that we got is actually a shop drawing from the tunneling contractor, and on that shop drawing it tells us that the diameter of this screw conveyor is actually 762 millimeters. However, the largest boulder size or cobble that this screw conveyor can take is only 240 mil. So, for instance, if you take a 900 mil boulder that the machine excavated, by the time it gets through the screw conveyor and out into the muck cart, the maximum size is 240 mil. So as the consultant and our site inspectors looking into the muck cart, we see a 240 mil cobble, but we have no idea if that was previously a 900 boulder or a 2 meter boulder. And hence the industry issue here with paying for boulders when we're using pressurized phase tunneling equipment. So here we have a diagram, and on the left we have a diagram of the face of the tunnel boring machine, and on the right this is an actual picture of the machine after it was retrieved from its first tunnel drive. I'm showing this slide just to emphasize that the largest openings you can see here in the face of the tunnel boring machine is 240 mil. And this is to protect the screw conveyor as material passes through the face of the machine and it comes to the inside of the machine. So I think now that we have a good understanding of why we can't physically see or quantify boulders with pressurized phase machines, maybe let's take a look at the alternative pay item that we developed with the region and the contractor during the first of the 3 tunnel drives that we noted earlier. So what was the goal for this alternative pay item? So we wanted to derive a fair and equitable payment for exceedances in the baseline quantities for boulder obstructions and or formations, like i.e. if the boulders were in clusters. We wanted to use the existing mining information to derive baseline push times / tunnel boring machine advance rates in the various soil types encountered. And as previously mentioned, we had 3 separate tunnel drives to complete, and we developed a pay item with information from the very first tunnel drive. So that was the advantage we had in this case. We had actual field data to derive a fair and equitable pay item. And lastly, we wanted to compensate the contractor for delays as a result of encountering obstructions rather than paying for the actual removal of the obstruction. So in other words, we wanted to compensate the contractor on a time basis rather than a boulder volume basis, because that is what we could equate at the time. So what was the challenges we had to overcome? So defining what constituted an obstruction without visually seeing the obstruction, that was the first challenge that we had to overcome. Accurately gathering the tunneling data in the field to determine push times and advance rates was a significant effort on behalf of the consultant and the region, because we had to have full-time inspectors actually situated within the tunnel boring machine to gather this data. And then we had to alter the pay item during construction, but still utilize the Boulder distribution numbers provided in the baseline report as part of the tender. So we still wanted to use the geotechnical baseline report as a basis in which to determine how much we needed to pay the contractor and to determine if there was exceedances in any particular Boulder bucket, as we said earlier, or Boulder quantity. So what information did we have available to develop this pay item? So we had the geotechnical parameters from the geotechnical baseline report, which included, as we said previously, the quantities, the soil conditions, the clogging potential of various geotechnical design information. From the first tunnel drive, we were also able to gather TBM operating parameters, including the advance rates, the force, base support pressure, the revolutions per minute, the thrust force on the cutter head torque, and the segmental build times. And finally, we had tooling and maintenance records available to determine if we could determine if the contractor was operating and maintaining their equipment, and in particular the cutter head in accordance with industry standards. For instance, if they weren't maintaining their cutter head, and then that directly resulted in slower mining times, like that would not be something that the region would be responsible for paying for. So we wanted to make sure we had a fair baseline, and we were dealing exclusively with boulders and not with variations in how the contractor was operating their machine. So for the analysis, let me start off by saying our analysis was prepared under the assumption that the size frequency histogram that we derived from the Shepherd Subway project was an accurate reflection of the halting glacial tills. And this was agreed between the client, the consultant, and the contractor. So this was the basis of how we proceeded forward. We recorded the tunnel boring machine push/penetration rates for each of the segmental liners. And these were recorded under the normal thrust and torque, and we plotted these on a graph. So the TBM, as I said previously, the TBM operator and our site inspector were within the tunnel, and they would record whether there was a boulder present in the ground or not during each push of the segmental liner. And they would determine this from like the sound, TBM roll, spikes in the thrust force, vibrations in the machine. And this was very important to help us develop a baseline and advance rate for the TBM under normal operating conditions. It was less important that it was extremely accurate or important that the operator and our inspector agreed on every single push. But over that kilometer, we wanted to make sure that there was enough drives where the operator and our inspector did agree that there was no boulders present, so we could set a baseline, and that was the basis for proceeding with our analysis. So the push time per segment were created for each boulder category, and it was based on the form that you can kind of see at the bottom of the screen there, and this is purely based on TBM operating parameters. And these operating parameters was a shop drawing submittal requirement that we required at the time of tender. So under normal operation, which would equate to normal torque of the tunnel boring machine, the contractor had noted prior to doing any tunneling that they would be operating at 4.4 revolutions per minute and an advance rate of 12 mil per revolution. So we had baseline schedules to check this against, and we had TBM information to check this against. So we did set this as our baseline. And from this, we could derive that when the tunnel boring machine was mining through the ground with no boulders present, that had been determined by the operator and our site inspector, the machine would advance at a rate of 52.8 mil every minute, or that equates to 23 minutes to install one segmental liner, which measured 1.2 meters. So 23 minutes was now established as the baseline. It was the minimum amount of time that the contractor could mine the ground prior to installing the segmental liner. subsequently, we done the same thing for determining when there was boulders. So when the TBM encountered boulders, the torque would increase. The smaller the boulder, there'd be a slight increase in torque, and then as it approached the 1 meter size boulders, the machine would kind of reach maximum torque. So again, from the shop drawings, it was evident that when they were going to hit a boulder, they'd go to max torque, and it would be 2.1 revolutions per minute. And this would result in a loss of advancement from 12 to 4.8 millimeters per revolution. I'll get my trusty pointer out here again. So, as I said in the previous slide, we did take all the information from the first drive, and the contractor demonstrated that 23 minutes was indeed their base push time under normal operating conditions. So the x-axis here is literally every push on the tunnel drive. This is just one snipping of one graph, but I thought it was a good representative graph just to show you guys. So each of these on the x-axis does represent each push, and the y-axis does represent push times. And you can see here there is a baseline, and each of these numbers will say 23 minutes, and that was the established push time. And you can see for 90% of the tunnel, 23 minutes was achieved. So we can see all these abnormalities was because the TBM encountered like maybe an unforeseen condition. It took longer to mine that segment, and hence the push times went up. So our analysis was to try and compare these push times to the boulder distribution determined as part of the geotechnical baseline report. And so based on the formulas from the previous slides, we derived that on average, an additional 15 minutes was required to mine boulders that increased in size, like in those 150 mil increments. So as you look at the slide here, you'll see we start to equate then that we'll take, for example, a 750 mil to 900 mil boulder was taken to Contractor 46 to 60 minutes. And the difference between each of these buckets is approximately 15 minutes. And then that was based on that formula that we previously showed, based on advance rates at a lower torque, assuming that they were encountering a boulder for that entire time. So the table tabulates the push times, and it shows how it puts the mining times into each category. So by equating the push times to particular boulder sizes, it is an estimation. So the times that we determined from a roundtable discussion with the owner, the contractor, and the consultant, from data that we had from the first tunnel segment, was determined to be the most fair and equitable way that we could proceed. And it's important, again, just remember for this analysis, we did assume that the Shepherd subway tunnel information was relatively accurate for the ground conditions. So we used a similar histogram to change the boulder sizes to push times. So now that we'd established a mechanism for measuring downtime rather than boulder quantity, how did we compensate the contractor accordingly? So based on time and material, the tunnel and operation costs were derived, and it came up to us at $68.48 per minute. And this was all derived from time and material sheets that was submitted. There is Ontario labour rates and industry standards for equipment, so it was relatively easy to determine this number. Mining times are swapped in for the boulder histogram numbers, and we compared these against the baseline. And where there was exceedances in the various boulder categories, the contractor was compensated at the $68.48 per minute rate, but only for each minute over the 23-minute baseline. So if we take, for example, we refer to pointer here, sorry. We'll refer to this 450 to 600 mil and this 37 number. The GBR said for the tunnel drive between 113 and 114, for the length of the drive, the contractor can expect to hit 37 boulders in the size range of 450 to 600 mil. And through our analysis, we changed that 450 to 600 mil boulder category to minutes. Now that the minutes that we said was 28 to 35 minutes. So every time there was a push time for a segment liner between 28 and 35 minutes, we equated that the contractor was hitting the boulder between 450 and 600 mil. So the first 37 occurrences that happened, this was at the contractors. This was the baseline, so the contractor just had to take this as base cost. So on the 38 boulder, we would pay the contractor for every minute over the baseline 23 minutes at that $66 rate that we derived at on the previous slide. And then for subsequent tunnel drives, the contractor had to illustrate that they could still complete a 1.2 meter drive in those 23 minutes. We effectively made them establish a baseline for each subsequent tunnel after this first tunnel that we based all our analysis on. So in conclusion, this method was relatively successful. It was successfully used on the remaining 2 tunnel drives of the project. There was a lot of boulders and there was some cobbles, but we didn't actually exceed the geotechnical baseline report on the remaining 2 drives. So our assumption that the Shepherd Subway Tunnel analysis could be used here was correct. Continuous inspection is required from the consultant team. So like I said before, we did have to have a site representative in the tunnel at all times. Access to the tunnel tax system would have been beneficial. So the tax system is just the computer system that the TBM operator sees, and it has all the information on it. So if we had had call it a read-only viewing rights to this would have probably alleviated the need for us to have a representative in the tunnel at all times. So I think we will definitely include this on the next projects. I think it's important to note that boulder sizes cannot accurately be determined based on inferred mining times, but in this case, it was an agreed fair and equitable way of compensating the contractor. And going forward, contract should include for downtime and hours rather than boulder removal volume as it pertains to pressurized phase tunneling. So as we move on, we are going to, we are going to take a look at putting in hours and time rather than boulder volumes. So I'd just like to acknowledge Joseph from the region of Halton, who was instrumental in developing this analysis and also having an open mind to sit down and come up with a fair and equitable way of compensating the contractor when these pay item issues did arise. And from the associate engineering team, I would just like to thank Brandon Gorr, Joanne Verseegen, and Andrew Morton, who are instrumental in crunching the numbers and providing some good feedback. So with that, I thank you all for listening, and we'll open it up for questions if we still have time.
We are running a little short on time, but I think we can maybe take just one question. VJ here asked, if boulders are crushed and not recovered, is there a need for a separate pay item to compensate the contractor?
Well, it's that old saying, right? Time is money. So if the contractor is taking 5 times longer to mine through a boulder, somebody has to pay for that time, right? And I think this is what has been established in a lot of papers, and particularly I think the North American Society of Trenchless Technology has dealt with this on a number of occasions. Like the contractor definitely has to be compensated, because if it's taking him 5 times longer to go through a boulder, his tooling on the front of the machine is wearing down, it's harder on the machine, and plus if it's costing the contractor $66 for every minute and it's taking him 5 times longer, he didn't account for this at the time of tendering.
Thanks, Cian. Thanks, everyone. We'll see you soon.